All right, second half of 7.7. For section 7.7, the majority of that section is L'Hopital's rule. But this is just one more little add-on that we want to look at of some indeterminate forms that we can use L'Hopital's to help us with if we kind of turn them around a little bit. So we've looked at indeterminate differences, indeterminate products, indeterminate quotients, and for this one we have an indeterminate power. Now, what is a power that we cannot figure out what it is? We can't determine. That would be something like 0 to the 0, because remember 0 to the 0 is undefined, infinity to the 0, or 1 to the infinity. Now, I know we think that, like 1 to the infinity, that seems like a no-brainer. Like, infinity is just a concept getting larger and larger without bounds. So if you have 1 to the 1, that's 1. 1 to the 10 is 1. 1 to the 100 is 1. 1 to the 1,000 is 1. 1 to the million is 1. That's just going to be 1, right? You would think, but no. We actually have an example today where 1 to the infinity is not 1, it's e to the 4th. So you cannot treat infinity like a normal number. It does not behave that way. So if you have like these last two guys here where you have an infinity in there, they're not necessarily going to behave like you think they would. Sometimes they will, but sometimes they won't. And so we need another way to approach this. So if I have the limit as x approaches a of f of x to g of x, and I have one of these indeterminate powers, here's what I can do with that. Step number 1, I'm going to rewrite my limit. Now, there's a very formal proof of this in your textbook as to why this method works, but just to give us an informal, kind of logical, intuitive understanding of this, remember when we studied logarithms and we said that if you had something raised to an exponent, that you could pull the exponent out in front of the logarithm, right? So I'm going to insert a ln in front of my function. That will then give me the right to take what was my exponent, g of x, and move that out in front and say the exponent times that natural logarithm. Okay, how can I just throw a natural log into my problem? Well, what would undo a natural log is an exponential, right? So when I get that limit, I'm going to go back and put in the exponential to balance out that natural logarithmic. So that's the informal gist of it. So step number 1, we're going to take our product, power. We're going to identify which is the base and which is the exponent. So we'll come over here and say exponent ln base and evaluate that limit. If we can come up with an answer for that limit, then the answer to our original problem will be e raised to that limit. Let's look at a couple. All right, so for the first one, we have the limit as x approaches 0 from the right of x to the x. So if I put 0 in here, that's going to be 0 to the 0, right? So that's one of those indeterminate powers. So I need to identify what's f of x and what's g of x. In this case, pretty straightforward since the base and the exponent are the same thing, right? So my exponent is x and my base is x. So step number 1, I'm going to rewrite my limit. The introduction to it stays the same. The limit is still x is approaching whatever I was approaching, so it's still 0 from the right. And then I'm going to do the exponent ln base. So our exponent was x, ln, our base was x. All right, so now let's see if we can evaluate that limit any easier than we could evaluate the last one. So if we put 0 into this guy, of course, is just going to be 0. If you think about what the natural logarithmic function looks like, this is the graph of a natural logarithm, right? So as you approach 0 from the right-hand side, that would go to negative infinity. So I'm going to end up with 0 times negative infinity, and that is one of our indeterminate products. So that takes us back to the first part of this lesson. In the first part of this lesson, we said if you had an indeterminate product, if I could find a way to rewrite that product as a quotient, I might be able to get an indeterminate form that I could use L'Hopital's on. So the way that we were rewriting the product as a quotient was instead of multiplying, like in this case, instead of multiplying by x, we said multiplying by x was the same thing as dividing by the reciprocal, right? So instead of multiplying by x, I could divide by the reciprocal of x, which is 1 over x. Now think about that. If you take ln x and you divide it by 1 over x, that's ln x times x over 1, right? That's still x ln x. I am not changing what I'm taking the limit of. It's the same thing. I'm just rewriting it in a different form. Instead of multiplying, I'm dividing by the reciprocal. My whole purpose in doing that is that maybe, just maybe, that will be one of those indeterminate forms that I could use L'Hopital's on. So let's check and see. So I'm going to go back and put 0 in from the right. We already talked about what that graph looks like and the fact that that would go to negative infinity. In our denominator, though, if I'm approaching 0 from the right, okay, now think about it, for 1 over x, the 1 is staying the same, but the denominator is getting smaller and smaller and smaller. So what is 1 over x doing? Getting bigger and bigger and bigger, right? It's increasing. So if this is getting bigger and bigger and bigger without bound, then it's going to go to infinity. So yes, that is one of those indeterminate forms for L'Hopital's. So I can use L'Hopital's, and remember my justification is that little h on the equal sign that shows I've taken L'Hopital's. So I can say the derivative of ln x is 1 over x, and the derivative of 1 over x, that's just x to the negative 1, right? So that would be negative 1 x to the negative 2, or negative 1 over x squared. Anytime we're evaluating a limit, we always want to see if there's a way to simplify it before I start plugging numbers in or anything else. So for this one, absolutely I could simplify. If I have 1 over x divided by negative 1 over x squared, that's 1 over x times negative x squared over 1, right? So we would end up with just negative x. Much easier to work with there. And then this is well behaved. I can use direct substitution and plug in my 0, and I get 0. So that was step number 1. Step number 2 says if you were actually able to come up with a limit for that first part, then your answer to your original limit will be e to that number. So our answer then is going to be e to the 0, which is 1. So we took a limit that initially was indeterminate and we rewrote it in such a way that then we were able to take the limit and figure it out. All right, look at another one. Oh, one other thing about this, if we throw x to the x in our calculator and look at the graph, as you approach 0 from the right, that does appear to be going to positive 1. So that graph backs up the algebraic work that we just got as well. All right, let's look at another one. For this one, we have the limit as x approaches 0 from the right of 1 plus sine 4x to the cotangent x. All right, so let's start with plugging in 0 and see what we get. If we put in a 0 right there, 4 times 0 is 0. So I would have sine 0. The sign at 0 is 0, so I would have 1 plus 0, so that would just be 1, right? So again, if I put 0 into this guy right here, I'm going to get sine of 0, which is 0, 1 plus 0 is 1. So this whole guy right here is 1. If I look at cotangent and I say, okay, the limit as x approaches 0 from the right of cotangent, this is what the graph of cotangent looks like. So as you're approaching 0 from the right-hand side on that curve, it's going off to positive infinity, right? So that would give me 1 to the infinity. And this is the one that we were talking about a little bit ago that we said, you know, by logic, it seems like that answer should be 1, but it is not. So let's look at then, if it's an indeterminate power, how I can figure it out. We need to define what is f of x and what is g of x. F of x is our base, g of x is our exponent. So for us, since g of x is our exponent, that'll be cotangent x. And since f of x is our base, that'll be 1 plus sine 4x. So step number 1 says you're going to find the limit using that same x and a value that you started with. So we still have the limit as x approaches 0 from the right. But we're going to do exponent ln base. So down here we have our exponent ln our base. Or if you want to think of it as g of x ln f of x, we've already defined those over here, so we could say g of x ln f of x. So just following that formula to get that first step. So hopefully we've created a limit that we could actually evaluate, because this one we could not. We've rewritten it in a way to see if hopefully that one we can come up with an answer for. So let's try it. I'm going to start by putting 0 in from the right. Now remember we talked about for cotangent, when you approach 0 from the right, that gave us positive infinity. Let's think about the second piece over here. All right, if I put in 0, that would be ln 1 plus sine 0. Sine 0 was 0, and 1 plus 0 gave us 1. So ln 1 would just be 0. So this whole natural log right here is going to be 0. So now I have infinity times 0, which is another one of those indeterminate products. And like we talked about up here, anytime you have an indeterminate product, you want to try and rewrite it as a quotient like we did in the first half of this lesson. We rewrote it as a quotient by, instead of multiplying by something, we divided by its reciprocal. I'm not really interested in trying to come up with a reciprocal for this mess, but coming up with a reciprocal for cotangent is really easy, right? What's the reciprocal for cotangent? Tangent, right. So I'm going to rewrite this, instead of multiplying by cotangent, I'm going to divide by its reciprocal, tangent, and then I'm leaving this natural log alone that I already had there. So this limit is identical to this limit. They're equivalent because dividing by tangent is the same thing as multiplying by its reciprocal cotangent. Why did we rewrite the product as a quotient? Because we're hoping it's one of those indeterminate quotients that we could use L'Hopital's for. All right, so let's try. Let's put 0 in. So we've already gone through the discussion. Remember that ln 1 plus sine 4x, we've already said would give us 0 in that numerator, but I wrote it back out for you again. You don't have to write all of that out. You've already got the 0. And then down here in the denominator, if I have the tangent of 0, tangent is sine over cosine. So sine at 0 is 0, cosine at 0 is 1. So yes, we do have 0 over 0, which in this case is actually a good thing. That's what we were hoping for, so that we could do L'Hopital's. All right, so if I'm going to use L'Hopital's, then I'm going to go through, I'm going back to, this is my limit, right, that was indeterminate. So according to L'Hopital's, I'm going to take the derivative of the numerator, and I'm going to take the derivative of the denominator. Let's start with the denominator since it's a little easier, right? What's the derivative of tangent? Secant squared, right. So I've got my h over here showing I've used L'Hopital's for my justification. I've done the derivative of the denominator. Now let's think about the derivative of the numerator. Remember, when you have the natural log of a quantity, that answer is going to be the derivative is going to be a fraction, where the original is in the denominator and the derivative is in the numerator. So we could go through then and we could say, okay, if I have the natural log of 1 plus sine 4x, the derivative of that is going to be the 1 plus sine 4x in the denominator and its derivative in the numerator. All right, so let's think about the derivative of 1 plus sine 4x. Derivative of 1 is 0. Derivative of sine 4x would be cosine 4x, but I'd have to use chain rule. Derivative of 4x is 4. At this stage of the game, we understand why this is one of the last lessons that we cover in the year, because it feels like we've covered half of what we've learned all year long in like one problem. It's just crazy. All right, so now let's see if I can evaluate this limit now that I've used L'Hopital's. So I'm going to go through and plug 0 in for every one of my x's. So 0 in for this x, 0 in for this x, 0 in for this x. All right, cosine at 0 is 1. So 4 times 1 is 4. That's off to a good start. Sine at 0 is 0. So 1 plus 0 is going to give me 1. And secant of 0 is 1. Because secant's 1 over cosine, right? Cosine at 0 is 1. 1 over 1, 1. So I end up with 4. So again, we took a limit that when we started, we were not able to evaluate. We have rewritten it so that then we were able to find the limit. That was step number 1. Step number 2 is, if you're actually able to come up with a limit, then your answer to your original problem will be e raised to that limit. So the answer to our problem is e to the 4th. And remember, in the beginning, we were sure that it was 1, right? All right, so here is our homework for tonight on pages 493 and 494. All right, so we want to look at section 8.5 today. Section 8.5 is applications of these things that we have been doing with our matrices and determinants and inverses and that type of thing. At this stage of the game, I'm not as concerned with can you add two matrices as I am with can you apply it to whatever it is that we're trying to get that matrix to do for us. So at this stage of the game, you've already proven to me that you can do all the matrices by hand. Now I want to go through and show you how to do everything that we've done in this entire chapter on the calculator. So we've already done a couple things on the calculator. I showed you how to put those matrices in, and I showed you how to find the inverse of a matrix, but we want to go back and catch all of those other things as well. So we're going to use the matrices that we have here on our screen for A, B, C, D, and E. And you'll notice that we're going to use multiple operations with each of those matrices. So when we saw how to load these into the calculator earlier in the chapter, we talked about two different ways that you could load them. You can put them on the main screen with that new operating system in the math print if you're just doing like one matrix at a time. But if you're going to use the same matrix over and over and over again, it's probably better to go ahead and load it into that matrix menu. So let's look at that. Okay, so I'm going to go to that matrix menu, and I asked you to go ahead and load in those matrices from A to E, but again, the way that we did that before, just for review, I would, if I'm on matrix A, I could go over to Edit and select it, and then I can tell it anything I want. Like if I want to have a 4 by 2 matrix, as soon as I give it that order, then it will reset that matrix for what I want. So we do want that 2 by 2 matrix that we had in the notes, so I'll go back and tell it 2 by 2, and then you would go through and say 3, enter 2, enter 1, enter 4, enter to enter that matrix, and then we can quit out of that. Okay, so the first thing that we have on that note sheet is that we want to add a couple of matrices. We were working with adding, subtracting, scalar multiplication, and matrix multiplication in section 8.2. So let's go over those. For the first one, we want to add matrix A and matrix B. So I'm going to go get the names. So I'm going to go to my names column, and I'm going to stick with that very first one right there for matrix A. And then plus, go back to matrix again. And this time I'm going to choose number 2 for matrix B. Now, when I try and add matrix A and B, matrix A is a 2 by 2, matrix B is a 2 by 3. Is that going to work? No. Why not? They have to have an identical order, right? You cannot add or subtract matrices if their order is not exactly the same. So what happens on the calculator if I try and do that? It's going to give me an error message, but I love it that when they give me the error message, they also give me a clue as to what I'm doing wrong. They're telling me your dimensions don't match. For what you're asking me to do, you don't have the right dimensions. So that would prompt me to go back and look at it and go, oh, wait, I'm trying to add a 2 by 2 and a 2 by 3. I can't do that. Their orders have to be the same. So let's instead go back and try to add matrix A and matrix D. Since both of those are 2 by 2s, they have the same order, I should be able to do that. So I can go back and say, okay, let's choose matrix A plus matrix D this time. Yeah, I didn't like that one. Come on. Try that again. Matrix D. So now it has no difficulty at all adding those two matrices because they have the same order. All right, the next thing on our sheet that we want to do is A minus D. Now, remember that you have that entry button down here on your calculator, that if you do second enter, it'll retype the last thing that you had on your screen. So if I want to take those same two matrices and just subtract them this time, it's a whole lot faster. Instead of having to go back and pull those names again, just come in here and type a subtraction sign on top of the addition sign. So then it goes through and subtracts those two matrices. All right, then we talked about matrix multiplication. And we said that your order does not have to be the same in order to multiply matrices. What does have to be the same? Yes, the column of the first one and the row of the second one. The inside numbers have to be the same in your orders. So, of course, if I try and multiply A and D, that's going to be fine because their order is identical. Their inside numbers are the same. So I can go through then and say second enter to retype what I just had. And again, I'm just going to go back and put a multiplication sign on top of that subtraction sign. And it has no trouble multiplying those matrices. When I first look at it, though, I might think that it was doing something wrong because it multiplied matrix A times D and it just gave me matrix A. Why did it do that?
Because it's the identity matrix for D.
Because it's the identity matrix for D. Exactly. 1, 0, 0, 1. You multiply anything times the identity matrix of multiplication, you get what you started with. That's why it's called the identity. All right, then let's see. Could we multiply matrix A times B? They're not the same order. Can I multiply them?
Yes, you can.
How come?
Because
the inside numbers are the same, right? I have a 2 by 2 and a 2 by 3. So since the inside numbers in the order are the same, then I can multiply. So I'm going to do second enter again, and then I can back up and just put B on top of D. So again, anything that's just a little bit of a time saver for us. The outside number tells me the order of my answer. And if you'll notice, when I multiplied A and B, the outside numbers were 2 and 3. So, yeah, I'm getting a 2 by 3 as my answer. All right, what if I go back and I multiply matrix B times A? Can I multiply matrix B times A?
No.
No, why?
Because the inside numbers are
Outside numbers and inside numbers.
All right, if I multiply matrix B, which is a 2 by 3, times matrix A, which is a 2 by 2, the inside numbers aren't the same, right? Okay, what does that look like on my calculator? Well, if I ask my calculator to do matrix B times matrix A, which we just said it won't be able to do, again, it's going to give me that same error message that says your dimensions don't match. For the skill that you are asking me to complete, your dimensions are not correct. Go back and check them. Okay, so it'll kind of give us a prompt of not just that we're doing something wrong, but what we're doing wrong. All right, then we can do scalar multiplication. We did that in section 8.2 as well. That's just where we take a number, like in this case 2, and we multiply it by a matrix. I'm going to multiply it by matrix B. So it should double every value in that matrix, and it does. We have already done inverses in section 8.3. I showed you how to put those inverses in your calculator. You can only find the inverse of a square matrix. So if I tried to put in something that was a non-square matrix, I would get an error message. And remember that if something is not invertible, meaning it doesn't have an inverse, then it's singular. And so that's typically the error message that I will get if I try and find the inverse of something that doesn't have an inverse. It'll say error singular, and that's just telling me this is not invertible. So in this case, we're going to use the 3 by 3 that we set up for matrix C. So I'm going to go to C, and then I'm going to ask it to do the inverse. And we did this before, but we did not get craziness like this. What is that? Well, see the little arrow right here? That just means your matrix keeps going. This is your first column right here. If I use my right arrow button, there's my second column. And keep going with my right arrow button, there's my third column. The problem is the answers that I'm getting are repeating decimals. It would be a whole lot cleaner if this were in fraction form instead of in decimal form. So just like you can take anything else on your calculator and switch it from a decimal to a fraction in the math menu, you can do it with a matrix as well. So if I tell it, take that decimal answer I just got and switch it to a fraction, then it's a lot easier to work with. Looks a little more normal because I've got the fractions instead. All right. The next thing we want to look at is how to find the determinant. In section 8.4, we did determinants of square matrices, 1 by 1s, 2 by 2s, 3 by 3s. It did have to be a square matrix to find the determinant. So I'm going to go back to matrix C again since that was a square one. So we can go back. Now, we're going to have to approach this a little differently than any of the other operations that we've done so far. We've worked in names and we've worked in edit, but if I want my calculator to perform a mathematical operation on a matrix, then I need to go to the math menu. So I'm going to go over to math, and it's actually faster to scroll up than it is to scroll down to get to to some of these things. Like you'll see down here, some of the things we'll use in a moment, row echelon form, reduced row echelon form. You could also here add a row to another one, or switch two rows, or multiply a row by something, or multiply by a row by something and add it to something else. That's those elementary row operations, right? But when you go to math, the very first item in that math menu is determinant, and that's what we want here. So I'm going to choose determinant, and then I'm going to ask it to find the determinant of matrix C. Now, C is a 3 by 3. Yesterday we did 3 by 3s by minors and cofactors and by diagonals. And think about how long it took to do it either way. I mean, it wasn't like an instantaneous kind of thing. But look how fast our calculator can do it, like literally a fraction of a second. Now, hang on to that -3 because we're going to use that in example number 1 today in just a minute. All right, last thing that I want to show you, we're going to use in example 5 in today's lesson. Back in section 8.1, we spent a lot of time using elementary row operations to put something in row echelon form or reduced row echelon form. We were using it to solve systems of 3 equations with 3 unknowns using Gaussian elimination with back substitution and Gauss-Jordan elimination. Gaussian elimination, putting something in row echelon form with those elementary row operations, that is not a unique thing. The elementary row operations you could do by hand or on your calculator, but the row echelon form that you get on your calculator is going to be different than the one that you have on your paper or that the person beside you might have on their paper, and yet they could still be right because it's not unique. But reduced row echelon form is unique. That means there is only one of those. All of us would get the same answer. It would all lead to the same solution as well. So that's preferred, but that takes longer, right? Well, not if I have my graphing calculator. If I had a system of 3 equations with 3 unknowns and I wrote an augmented matrix in it, it would look something like what we put in matrix E. So I want to go back and I want to ask my calculator. I'm going to go over to math, and again, it's faster to scroll up. I'm going to scroll up to reduced row echelon form. So I'm going to ask my calculator to do reduced row echelon form of matrix E. And again, remember, if I'm doing this by hand, we're talking half a sheet of paper in 10 minutes, right? Fraction of a second. Don't like the decimals? Okay. Switch it to fractions. It can give it to you that way as well. So now, solving a system of 3 equations with 3 unknowns is as simple as typing the augmented matrix in your calculator, hitting a couple of buttons, and it shoots it out instantly. Okay? All right, so just for review, these are the things that we were working on. Couple of reminders about them. When I tried to add A and B, I got an error message because the orders weren't the same. I had no trouble adding and subtracting A and D because their orders were identical. I was able to multiply A and D, but I got A as my answer, and that was because D was the identity matrix, and if you multiply anything times the identity, you get what you started with. We were able to multiply A times B, but we were not able to multiply B times A, stressing to us again, A times B, not the same thing as B times A in matrices. So we used that specifically when we were solving a matrix equation, and we had to find the inverse of A and multiply it times B, and we stressed that you had to do it in that order or you would not get the right answer. Right? And then scalar multiplication, finding the inverse, that has to be a square matrix to find the inverse. Finding the determinant, that has to be a square matrix to find the determinant. And again, we're going to use that in just a second in example number 1. And then finding reduced row echelon form for a matrix, and we'll use that in example 5 today. We also mentioned that if you didn't like the decimal version, that you could switch it to a fraction and give the fraction version anytime maybe you got repeating decimals or something like that. All right. So section 8.5, now that we know how to do those things on our graphing calculator, for tonight's homework we are doing every problem on the graphing calculator. So we're doing all of these with our calculator. All right, so the first application that they give us on 599 is how to find the area of a triangle. And they tell me that if you know the 3 vertices of a triangle, then you can find the area of that triangle. Now think about that for just a second. So if we've got 3 points that are the vertices of a triangle, think about area formulas that we know for a triangle right now. 1/2 base times height. That doesn't do me any good because I don't necessarily know the base or the height of that figure if I just know 3 vertices. Heron's area formula works for a side, 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 but that requires that I know the length of all 3 sides, right? So what does that mean? That means that I get to use the distance formula between these 2 points to find the length of that side, and then use the distance formula again to find the length between these 2, and then use the distance formula again to find the length between these 2. So I've already done 3 problems just to get the length of the 3 sides. Then I still have to do Heron's area formula to find the area of that. So probably not the best way. So here on 599, they tell me if you want to find the area of the triangle and all you know are the 3 vertices, you can use a matrix to do that. I'm going to set up a matrix and then I'm going to take the determinant of that matrix. Here's how I'll set up the matrix. It's going to be the first point followed by a 1, second point followed by a 1, and then the third point followed by a 1. So in example 1, when they give me these 3 vertices, all I have to do is go through and say, okay, my first ordered pair was 1, 0. So I'm going to fill that in, 1, 0, and then I'm going to follow it by a 1. Second ordered pair will be 2, 2. So I'll put that one in and follow it by a 1. Third ordered pair was 4, 3. Put that in, and I'll follow it by a 1. What do these bars tell me to do? Find the determinant, right. At this stage, remember, I'm going to let my calculator do the tediousness for me. I'm focusing on the application. So this is the exact same determinant that we threw into our calculator a few moments ago and got -3. So now that area formula says do plus or minus 1/2 of -3. I'm not going to actually write an answer that says plus or minus. This is area. What does area have to be? Positive, right. It does also have to be square if they give me a unit, yes. So it's got to be positive. So that's the purpose of the plus or minus out here because there's no control over that determinant. Sometimes the determinant's positive, sometimes it's negative. So the plus or minus just means take 1/2 times the value that you get, and in this case 3/2, and if you need to multiply a negative by it because it's negative to make it positive, or if you need to multiply a positive by it because it's positive to make it positive, do whatever you need to do, but of course the area has to be a positive value. So in this case, we would be doing a -1/2 times a -3 to get the positive 3/2. So that would be the area of the triangle formed by those 3 vertices. We can take that same formula and use it to help us with something else as well. There are times that we need to know whether 3 points are collinear. Collinear just meaning that they're on the same line, right? And sometimes we can draw that out and it's obvious. Yes, they're on the same line. No, they're not. But let's say that I have a situation where I plot the 3 points and one of the points is just slightly above the line. I'm not really sure, like maybe I just need to be more precise. Maybe I need a straight edge. Or is that point really not on the line? I need a definitive way of figuring that out. And so here's what I can do. They tell me that 3 points will be collinear if their area is 0. Now, that makes sense if you think about it. If there are 3 points in a straight line, they don't encompass any region, right? So they would have an area of 0. But if they're not collinear, then they are going to encompass a region, and so we would get an area that was not 0. So if they give me 3 points and they say, are these collinear, I'm going to use that exact same area formula. If I get an answer of 0, then I'll know they're collinear. If I get any non-zero number, then I'll know that they're not in a straight line. They're not collinear. All right? So let's take these 3 points and let's set up that matrix again that we want to take the determinant of. So what's my first row going to be? Yeah, -2, -2, 1. So I'm just taking my first point and then following it by a 1. What's my second row going to be? And what's my third row going to be? Yes. So again, you would be welcome to throw that into your calculator and take the determinant. And you'll get negative 6. Now, if you notice, there's like a piece missing from the formula. They don't have the plus or minus 1/2 in front of it. Well, they didn't forget it, but what's half of 0? 0. What's half of non-zero? Non-zero, right? So the 1/2 is not necessary for you to be able to tell whether they're collinear or not. So they just dump that part out to save you a step, right? So when I do this determinant and I get an answer of negative 6, are those 3 points collinear? No, because if they were, I would have gotten an answer of 0. Exactly. All right, last thing that they give us on page 601 is Cramer's rule. Now, you did Cramer's rule in Algebra 2, so that'll be review for us. But Cramer's rule is just another way that we can solve systems of equations. So let's start with two equations with two unknowns. All right? If I have example 3, 4x minus 2y equals 10, and 3x minus 5y equals 11. I'm going to set up 3 matrices to take the determinant of. Okay? The first one is just going to be the coefficient matrix. So I'm going to pull out 4, negative 2, 3, negative 5. That's my coefficient matrix. I'll call that D. All right? Then I'm going to have a second matrix to take the determinant of. I'll call that D sub x. For D sub x, I'm going to replace the coefficients of x. Now, remember that was 4 and 3. I'm going to replace the coefficients of x with the only other numbers that I have. That was my constants. So the constants were 10 and 11. So I'm going to replace the 4 and the 3 with 10 and 11. All right? Then I have D sub y. D sub y, I'm going to go back to the coefficient matrix, and I'm going to replace the coefficients of y with the only other numbers that I have, and those are my constants. Now, each of those is just a 2 by 2. So to take the determinant of the 2 by 2, I could probably do it in my head. I wouldn't even have to write anything down. So I could go through and say main diagonal minus alternate diagonal. So I could say negative 20 minus a negative 6 is going to give me negative 20 plus 6, so negative 14. For this guy, negative 50 minus a negative 22 is going to be negative 50 plus 22, so that'll give us the negative 28. For this guy, 44 minus 30 is going to give me 14. Once I have those 3 determinant values, here's how I find x and y. X is just going to be d sub x divided by d, and y is just going to be d sub y divided by d. An easy way to remember that, not algebraically sound, but just a little mnemonic device to remember that, is if you canceled those d's out, you would just be left with x in the numerator and y in the numerator. So that's a good way to remember what those formulas are. So d sub x was negative 28, and d was negative 14. So if we do negative 28 over negative 14, that'll give us 2. And for y, d sub y was 14 and d was negative 14. So if we do 14 over negative 14, that'll give us negative 1. So there's our solution to that system, 2, negative 1. If I have a system of 2 equations with 2 unknowns, is that like going to be my favorite way of solving that system? Probably not. I mean, I'm probably still going to go back to elimination if I have my choice. But this is not so bad. I mean, literally the only work that I would have to do for this is maybe write out these 3 determinants on my paper. I could find the determinants in my head, and then I could divide in my head and go straight to my answer. So literally, this is the only work that I would have to write out. That's definitely faster than creating 2 XY charts and graphing 2 different lines and then trying to figure out their point of intersection. So it's just another option that we can utilize that, choose whichever method that we might want to work with. It also is helpful if I understand the system for a 2 by 2, then I can apply that to a 3 by 3 as well. So let's say I had a system of 3 equations with 3 unknowns. I could use Cramer's rule for that exact same way. I'm going to start by pulling out my coefficient matrix. I'm going to call that D. So here's my coefficient matrix right here. Because I have 3 unknowns this time, I'm going to need a d sub x, a d sub y, and a d sub z. So for d sub x, I'm going to replace the coefficients of x with the only other numbers I have, my constants. For d sub y, I'm going to replace the coefficients of y with my constants. And for d sub z, I'm going to replace the coefficients of z with my constants. Now, that means to do this problem, I got to do 4 3 by 3 determinants, right? There's no way I'm asking you to do that on a test or a quiz without your graphing calculator. So if I'm throwing those determinants into my calculator, that's going to be pretty quick. for me to come up with the 10, 8, negative 15, and negative 16. And then the formulas are exactly the same. I can come down here and say, okay, x is going to be d sub x over d, so that would just be 8 over 10, and I could reduce it. Y would just be d sub y over d, so that's going to be negative 15 over 10, and reduce that. And z is just going to be d sub z over d, so negative 16 over 10, and I could reduce that, and then I could write my solution. Here's my thing. If the only way to feasibly do this problem in a reasonable amount of time is to use a graphing calculator to do those 4 determinants, if I have access to a graphing calculator for a problem like this, that is not the way I'm solving it. Because now that I have that reduced row echelon form button on my calculator, here's what I could do. Remember back in section 8.1 when we would take a system of 3 equations with 3 unknowns and we would write the augmented matrix. And then we would do the elementary row operations to get it into row echelon form, take like half a page, 10 minutes. Heaven forbid we went on to reduce row echelon form, right? But now, if I can take that augmented matrix and throw it into my calculator, like we did in E, and with the press of just 1 or 2 buttons, have it do reduced row echelon form for me. Here it was in the decimal form, here it was in the fraction form. Look, x is equal to 4/5, y is equal to negative 3/2, z is equal to negative 8/5. I'm done. So if I have my choice of any method that we've learned up to this point, and I have a graphing calculator, that's definitely the way that I'm going. So on the test, I may require you to set up a Cramer's rule problem, but when you have a system of 3 equations with 3 unknowns and it actually comes to solving it, I'll let you solve it by any method that you want. So you could set it up by Cramer's, but solve it by the method of your choice, and I would suggest that reduced row echelon form. It's definitely fastest and easiest. Okay, so here's our homework for tonight, and here's our favorite part. I want you to use your calculator on all of these. Don't do them by hand. Do them all on your calculator. And then we're going to go back and continue with what we've been doing. Our challenge problem goes back to section 8.1, where we're doing the putting something in row echelon form by hand. We don't want to lose that skill, so we've been trying to do it repeatedly to maintain that for our test. We do have our quiz tomorrow over 8.3 to 8.5, and that quiz is non-graphing calculator. I need to see that you can do the inverses and the determinants and that type of thing by hand, and then for your test we'll have half the test where you're doing it by hand and the other half where you can do it on your calculator. Because you don't have your graphing calculator tomorrow, I'm not going to ask you to find the inverse of a 3x3 or the determinant of a 4x4 or larger, because I told you that I would only have you do those things with a graphing calculator. If you had a triangular matrix, though, you might have like a 4x4 that was a triangular matrix that you could do without a calculator because you're just multiplying the main diagonal. So you could watch out for that.